it was pointed out to me that I had actually missed part of this lecture. So this comes in after slide 8 on the adulteration section. So what we were just mentioning is that one can look for trace components in one essential oil that are not present in another essential oil as kind of an indicator to get this oil, that's two oils that are similar, to try to differentiate between them. But actually a better way is to look at chiral compounds. They tend to be very unique. One plant may produce one chiral form of a chemical, another plant may produce a different chiral form. Actually, if there's organic synthesis around a chiral center, you'll have a racemic mixture. So it's really a useful technique, and we can separate chiral compounds by gas chromatography. And some of the examples that we mentioned in class were looking at authentic bergamot oil and orange oil, and here we're looking at linalool. What is the chiral form of linalool in each of these? Certainly lactones and fruit juices, rose oxide and rose oil, and so on. So there is application of these. And so this is an example for linalool, is shown in the top figure. So differentiating authenticity of bergamot, and the bottom shows an example of passion fruit for pentanol, 2-pentanol actually. And so whether it's produced by a plant or whether it's produced as a racemic mixture. So again, very hard to replicate, very hard to make chiral isomers to spike, and therefore adulter. So it's a good choice. Next section we talked about was using mass spectrometry to identify adulterated products. And so you'll see two approaches here. This is an example of cassia. The major flavor constituent in cassia is cinnamic aldehyde. But the idea of adding synthetic cinnamic aldehyde, the synthetic material contains 400 to 500 parts per million of phenylpentadienyl, which is a byproduct of organic synthesis. So what you do is you look for trace amounts of this phenylpentadienyl. And so the next figure goes ahead and shows what cinnamic aldehyde looks like. It's top left. On the top right, we have the phenylpentadienyl as a contaminant of synthetic cinnamic aldehyde. And so what you do is you set the mass spectrometer up to look for key ions that are characteristic of this byproduct or contaminant. And you'll notice that the masses of 158, 129, and 128 are fairly unique ions, and they are indicative of, like I say, this contaminant. And so if we go ahead and do injection gas chromatography, monitoring mass 158, for example, we see there's a tiny peak on the left-hand side. If we look over at the right-hand side, we can see a larger peak. The right-hand side is a synthetic material. The left-hand side is in the essential oil. The same is true for mass 129. There's a small peak that's present in cinnamic aldehyde. But we can look at the adulterated or synthetic product. There's a large peak in 128. So essential oils that have cinnamic aldehyde in them, you can look for these three ions occurring at the right retention time as being indicative of being adulterated with synthetic aldehyde. Neroli is another one. Neroli depends very heavily upon linalool. Synthetic linalool contains 0.5 to 2% dihydrolinalool. It's not found in nature. It shouldn't be there. And so it's the same kind of mass spectrum in this case. So again, we're looking for dihydrolinalool. It has a mass of 138 and 73 as being indicative. It tends to elute someplace around at 32.4 minutes. And the two chromatograms, or mass spectral traces on the left, are an oil where there is no dihydrolinalool. You'll notice the absence of peaks at 138 and 73 at that proper time, the 32.5 minutes retention, where on the right you've got a synthetic linalool, and you find the dihydrolinalool being present. So again, looking for these trace components that don't come from nature is a good indicator of adulteration. In terms of coconut, naturally we find delta lactones. Most of the time we find adulteration with the gamma lactones. So different forms, different ring structures. Remember, the gamma lactones have a 3-membered ring. The delta lactones have a 4-membered ring. And so when we look for mass spectrometry and we can monitor just that ring structure, gamma lactones have a major mass at 85, while delta lactones have a major mass at mass 99. So again, we look at a chromatogram, looking at mass spectral ions, and we can find, the top chromatogram is the lactones in the flavoring material. The second line, or the middle line, is where the mass spectrometer is looking just for the delta lactones, and it certainly finds a delta lactone here, a delta lactone again a little later. But if we set the mass spec to look also for 85, we find there is the gamma lactones. So there shouldn't be any delta lactones in the sample. The presence of those delta lactones demonstrates the product's adulterated. Stable isotopes. Well, nature has a certain amount of carbon-13, oxygen-18, deuterium of mass 2. So normally, of course, we find C12, C16, and hydrogen mass 1, but nature provides some other of these isotopes, and they can be used to look for authenticity. And in this next slide, we have 3 different metabolic pathways that plants will tend to work under for their metabolism: Hatch-Slack, a CAM, or a Calvin. So different types of plants have slightly different metabolic routes. And the slightly different metabolic routes have a property of incorporating more or less carbon-13. So if you look over on the left-hand side, corn, sugarcane, millet, lemongrass, they all have Hatch-Slack metabolic pathways. This pathway doesn't have as much of the carbon-13 in it, and so you can get a measurement there. And if a plant material comes from pineapple, vanilla, or guava, okay, it falls in another category, or wheat, sugar beets, grapes, and citrus fruits. So you can look at the carbon-13, the ratio of carbon-13 to carbon-12, and know what type of plant a certain material came from. And so what we can do is we can look for these ratios. Now, stable isotope ratio analysis, that's a fairly old methodology. You basically isolate a pure component. You're questioning what's its carbon-13 to carbon-12 ratio. Problem is it takes 5 to 30 milligrams of a pure material. if you've got a complex mixture of chemicals and flavoring or in food, it's tough to get that much material. So the idea of getting the material, combusting it, and determining this ratio is really tedious. So lots of materials needed, and so we have a better technique that's available to us. And so we can start looking at this ratio fairly easily using the SIRA methodology. It's again GCMS based. And this has just been applied to vanilla, specifically vanillin. There's much more natural vanilla sold in the marketplace than there is vanilla beans grown. So it's a real target for adulteration, especially recently when the costs have gone up a great deal due to weather conditions. And so there's some data here. What's vanilla from Madagascar, kind of the gold standard? Vanilla from Tahitian. Well, vanillin can also be made from lignin, eugenol, or glycol. And what's the carbon ratio in these plant sources? Notice a much higher negative number. So if we would think we've got an adulterated vanilla product, we can go ahead and look at the vanillin isotope ratio, and if it's not between 18 and 20, it's been adulterated. So it's a fairly simple way. The bad news is that adulterers also are aware of this. And so what have they done? This is a picture of course, vanillin. They put a little carbon-13 up here on this top group. And by putting a little carbon-13 out here in their synthesis pathway, they can now fool our testing methodologies. And so this shows up in the next slide, which is then also a way to go ahead and track this out or find out if they have adulterated. What now the police do, the police so to speak, is they look at the carbon-13 ratio only on that carbonyl group. And you'll find a bourbon vanilla, which of course is the premium, so minus 25.7. But lignin is to minus 37.3, but if it's been adulterated, it shows up as being a plus 17. So basically, by monitoring the carbonyl, you can tell whether the vanillin came from a vanilla plant or if it came from lignin, which was then chemically modified to add this carbon-13 group onto that top group. We use carbon-13 ratios to look at adulteration in other materials like honey, maple syrup. Can two very high-value products up there? Well, are they adulterated corn syrup, sugar cane, sugar beet? You'll notice corn syrup and sugar cane wouldn't be good. They differ very greatly in your stable isotope ratio. However, you could adulterate honey or maple syrup with the sugar beet. So, interesting. And the idea of this deuterium distribution, looking at the deuterium-hydrogen ratio. Okay, the Earth is spinning. It's like a centrifuge. Deuterium tends to be thrown out along the equator, and so there is a gradient of deuterium, natural deuterium in the environment, highest at the equator, smallest at the poles. And so basically, you can do deuterium-hydrogen ratios on wines, juices, any kind of plant material, and you can tell where this was grown. Was it grown close to the equator, or was it on, of course, either side of the equator, where we have less deuterium ratios? And so it does help us in knowing where a wine or an olive oil or something else was grown. Is it authentic? And again, we've got some nice methodologies that have come out for looking at deuterium-hydrogen ratios. It actually can be done very, very quickly these days. So, again, stable isotopes, very helpful in knowing place of origin or plant source that's used to go ahead and adulter an essential oil or flavoring. The last isotope, of course, is carbon-14. Carbon-14 is radioactive carbon, and petroleum sources no longer have any carbon-14 radioactivity. So if we synthesize, do typical synthesis from petrochemicals, the flavoring material that comes out is going to have no carbon-14. The interesting thing is that over time we've been experimenting with hydrogen bomb testing, and so we've got a good history of what's the carbon-14 in the environment and in plants year by year for the last, well, whatever, since we started testing hydrogen bombs. How's that? And so we can actually pick out a year of the harvest. So carbon-13 ratios can tell you where something is harvested. Carbon-14 ratios can you tell when it was harvested, or if it's harvested at all. So some pretty neat things. The problem is carbon-14 has historically taken a lot of material. And in fact, some people try to adulter by adding a little carbon-14 to synthetic products. So there's always a way to test something. There's almost always a way to get around it. The last example is looking at using HPLC for adulteration of lemon oil. Back when we talked about flavoring materials, essential oils, we talked about lemon oil and how the citral can be taken out of lemon oil, and then that would leave some flavorless terpenes. Well, let's take that flavorless terpenes, add a little citral to it, add a little UV absorbers added back, and people will sell that as a real lemon oil. So they take this cheap byproduct, steam stripping, clean it up a little bit, fortify it with citral, and add UV absorbers. And again, if you know the right UV absorbers, you can fool this quality assurance test. Here's some examples. But interesting, 1988, someone started looking at the oils in lemon oil in the UK and found out every sample of lemon oil was adulterated. And this is just an example of the chromatogram. So they got basically things in there as UV absorbers to fool us that are detectable by HPLC. So again, it's always a game. Someone adulterating and someone trying to catch them. When it comes right down to controlling adulteration, there are some good practices. One is buy from a reputable supplier. There's a reputable supplier really has a reputation to look after, and they're less likely to go ahead and adulterate a product. Look at the price. If somebody's offering you a price for a raw material that's too good to be true, it probably isn't true. And the idea, if you suspect something, don't buy it. That simply isn't going to pay off. So, interesting process. It's truly a game of cat and mouse, so to speak.